Hello, Mrs. Saunders here, and a very big and warm welcome to Calculus. So excited to be with you and to learn all the cool things that we have ahead of us. Before we dive into actual calculus, we're going to spend some time reviewing some of the pre-calc material to make sure we have a good solid foundation. And before we even dive into that, we're going to answer two questions. One, what allowed calculus to develop? And two, what are the advantages of combining an analytic and geometric approach in math? In 1637, the French mathematician René Descartes, that's this guy right here, revolutionized the study of mathematics by joining its two major fields, algebra and geometry. And then, with Descartes' coordinate plane, the geometric concepts could be formulated analytically and algebraic concepts could be viewed graphically. And the power of this approach is such that within a century, much of calculus had been developed. So calculus is sort of this marriage of algebra and geometry, which means everything you've learned in high school is now in play, which is kind of exciting and maybe a little bit scary also. But that's okay. I'll walk you through it. We're going to talk about solving things numerically, solving things analytically, and solving things graphically. If I asked you to plot these points, and I gave you a coordinate plane, you should come up with something like this. Now, why do we plot points? We can get an idea of what a graph will look like. So these points could be the line y equals x. They're in a nice linear pattern there. Or these points could also be on, whoa, that crazy function right there. So how do you know if it's on y equals x or if it's on this crazy function down here? Well, that's part of the problem with just plotting points or just looking at the numbers, because there's an infinite number of points on any given function, and just plotting a couple points can leave out some very important information. So now we're going to add an analytic approach on top of that. We can discover all kinds of things with an analytic approach, such as intercepts, changes in direction, symmetry, rates of change, asymptotes. And so what happens is you've got a numeric approach and an analytical approach, and when we marry those together, we come up with some graphic representation of a lot of cool information. So this is calculus. So again, we're going to start with some pre-calculus, maybe Algebra 2 review concepts, just to get you warmed up. Now, if I go through this too fast, just pause the video at any time. This is review, so I'm going to go a little fast. Let's talk about intercepts. An intercept is a point at which a graph crosses the x or y axis. An x-intercept can be called a root, a zero, a solution. Those are all synonyms. A y-intercept can be called a y-intercept. We don't really have a lot of synonyms for that. Maybe we just, I don't know, ran out of ideas. To find the x-intercept, you let y be 0 and solve for x. To find the y-intercept, let x be 0 and solve for y. Let's practice. So to find the intercepts of this graph, y equals x to the third minus 9x, first we're going to let y be 0 and solve for x. So I've got 0 equals x cubed minus 9x. I'm going to do some factoring here. Hopefully your factoring skills aren't too rusty. So I factored out an x, and then that x squared minus 9 is a difference of squares. So I have three possible roots or solutions or x-intercepts, -3, 0, and 3. To find the y-intercept, I'm just going to plug in 0 for x. So 0 cubed minus 9 times 0 is 0. That's what that graph looks like, and you can see there's the x-intercepts right there, and actually the y-intercept in the middle as well. Let's try this one, sine of x plus 1. So again, to find the x-intercept, we're going to set it equal to 0, let y be 0. And we're going to solve for x, so we'll subtract 1 from both sides. Now, how do you get the x out of that sine? So you're going to take the sine inverse, basically. So what angle gives you a sine of 1? 270 degrees or 3 pi over 2. And most of the time we're actually working with radians, not degrees in calculus. Then we'll find the y-intercept, so we'll just let x be 0. So the sine of 0 is 0. If you add 1 to that, you get 1. So there's the graph of that one. And we've got the x-intercept of 270, or 3 pi over 2, and the y-intercept of 1. Now let's talk about symmetry a little bit, because knowing the symmetry of a graph before you attempt to sketch it, or just even having it in your mind, is really helpful because you only need half as many points in order to sketch the graph. So a graph would be symmetric about the y-axis if whenever xy is a point on the graph, negative xy is also a point on the graph. A graph is symmetric about the x-axis if whenever xy is a point on the graph, then x negative y is also a point on the graph. And we would have symmetry about the origin if whenever xy is a point on the graph, negative x negative y is also a point on the graph. So how do you test for symmetry? Well, if you want to know if it's symmetric about the y-axis, you replace x with negative x, and then simplify to see if the equations are equivalent. If you're checking for symmetry about the x-axis, replace y with negative y, rearrange again to see if the equations are equivalent, and then finally, if you're checking for symmetry about the origin, replace both x with negative x and y with negative y, simplify, rearrange, and see if you get the same thing back again. So let's practice that. We're going to test y equals 2x cubed minus x for symmetry with respect to the y-axis and the origin. So to test for symmetry about the y-axis, we're going to take each of the x's, so anytime there's an x here, and we'll replace those with negative x's. So if we have a negative x cubed, that's going to stay negative, and then negative times a negative is positive, so we end up with y equals negative 2x cubed plus x. Now the question is, are those equivalent equations? Well, because of this negative right here and the positive right here, those aren't equivalent equations. So we know that this equation is not symmetric about the y-axis. Let's check for symmetry about the origin. So again, we take the original function. Wherever there's an x, we plug in negative x. Wherever there's a y, we plug in negative y. And then we're going to rearrange this, simplify it a little bit. So the right side is still the same as it was before, but we've got this negative. So if we multiply both sides by a negative, well, look what we get. We have equivalent equations now. So that means this equation, this graph, 2x cubed minus x, is symmetric about the origin. Points of intersection. So a point of intersection is a point that satisfies two equations. You can find points of intersection by solving simultaneously, or you can just graph it. So we'll start by solving these equations simultaneously. Let's take this first equation, and solve it for y. Take this second equation, we can solve it for y also. And because they're both equal to y, that means they are equal to each other. Now I can solve for x. Okay, let's get everything on one side, set it equal to 0, and we'll factor that. And so these guys are going to intersect at x equals -1 and x equals 2. So if I plug in -1 and 2 to either of the equations, then I can get the y values that go with it, and I have my 2 points of intersection. And if I graph it, oh look, I get the same. I get the same thing, so that's lovely. All right, rates of change. This is a big, big, big deal in calculus. A rate of change you might be most familiar with is slope. So the slope is the measure of the number of units a line rises vertically for each unit of horizontal change from left to right along this line. Whew, that's a lot of words. You might know that as rise over run. So there's rise, that's the change in y, over run, which is the change in x. So if you have parallel lines, the slopes are equal. So if you have one line that has the slope of 4/3, another line that's parallel to it will also have a slope of 4/3. Perpendicular lines have slopes that are negative reciprocals of each other. So if the first line has a slope of 4/3, its perpendicular line will have a slope of -3/4. Flip it and take the opposite sign. Equations of lines. There's 3 main equations of a line. There's point-slope form, slope-intercept form. This is usually a fan favorite in like geometry and algebra, and standard form. Now in calculus, we're almost always working in point-slope form, and actually sometimes you might see it looking like this: y equals m x minus x1 plus y1. We just take this guy and kind of move it over. That's another common version of point-slope form, so be ready to look at that. All right, next we're going to talk about asymptotes. An asymptote is a line that a curve approaches as it heads towards infinity. We can have vertical asymptotes. Those are vertical lines which correspond to the zeros of the denominator of a rational function. A rational function would be like a fraction. So if you look at this fraction here, we need to know, well, what are the zeros of the denominator here? So if you factor x squared plus 2x minus 8, you get x plus 4 and x minus 2. Well, the zeros of that denominator are x equals -4 and x equals 2. And so those are the vertical asymptotes right there, see that, of that graph. Horizontal asymptotes, they indicate general behavior usually far off to the sides of the graph. We sometimes call that end behavior. So I don't know if you remember this, but if you have a rational function, if the powers are bigger on the bottom, so x squared, see that's bigger than x to the 1, then you're going to have an asymptote of y equals 0. If the powers are equal, then this is fun. You just look at the coefficients of those leading terms, y equals 3/4. And if the power is bigger on top, so we've got 3 is bigger than 2, then you're going to have some sort of slant asymptote or infinity. We'll cover asymptotes more as we dive into some of the calculus topics, so consider this a teaser for now, and we're going to stop there. I'll see you next time for part 2 of Pre-Calc Review. Thanks for being here.